Hello students, I hope you are all doing good, and our today's topic is alternating current, NCERT section 7.5 and example 7.3 to 7.5. This is the disclaimer. So learning objective after this lecture, you will be able to learn how capacitors work with AC voltage, including how current and voltage relate to each other in the case of purely capacitive circuit, and understand the basic formula for capacitive reactance, which is XC. Understand how current leads voltage in a capacitor circuit. Okay, in purely inductive circuit we have seen inductive reactance. In capacitive circuit there will be capacitive reactance, and in inductive circuit we saw that current lags behind the voltage. Then now you will be able to understand that how current leads voltage in capacitor circuit, and how capacitors behave differently when connected to AC versus DC power source. Okay, so index of the topics that we are going to cover today is NCERT section 7.5, AC voltage applied to a capacitor, example 7.3, example 7.4, and example 7.5. So let's begin. So when a DC voltage is applied to a capacitor, it will limit or oppose the current as it charges. Okay, so when capacitor starts charging, voltage or any potential difference start building up on its plates. Okay, so it will limit the current flow through the circuit, or it will oppose the flow of current through the circuit. Okay, we will see that how it will react when there is a DC current. Okay, and in this section we are going to discuss in detail when this capacitor is connected to AC voltage, how will it behave, how will it react to that. Okay, so when the capacitor is fully charged, the current in the circuit falls to 0. We have discussed in the electrostatics also. Okay, we didn't deal with currents in the case of capacitor, we only dealt with charges. Okay, so that means when we are considering capacitor and a DC source, it will block the current when it is fully charged. Okay, a potential difference is created between its plates, and it will block the current flowing through the capacitor. Okay, so it will get fully charged. Until it will get fully charged, amount of current will decrease, okay, in the circuit. So initially the full current is flowing through the capacitor circuit. Okay, when capacitor start charging, voltage is start to build up across its plates. Okay, so then it will limit or oppose the flow of current in the circuit. When it is fully charged, the current in the circuit falls to 0. Now let's find out what happens when AC source is applied to capacitor. Okay, now this is the diagram, figure 7.7, in which a capacitor is connected to a AC source. Okay, consider a circuit with a capacitor C connected to AC source generating AC voltage V equal to Vm sin omega t. So voltage we have taken in all type of circuits, resistive circuit, inductive circuit, or capacitive circuit, we have taken same voltage V equal to Vm sin omega t. Okay, now AC voltage applied to a capacitor. Let Q be the charge on the capacitor at any time t. Okay, a capacitor is being charged, but it is alternating current. It is being charged and uncharged at after equal intervals of time. Okay, when current start increasing, it will get charged. When current will decrease, it is discharging again. Then current will start increasing in the negative direction, in the negative cycle. Then capacitor will get charged, but in the opposite sense. Okay, and then current will start decreasing in the negative direction. It will go towards the 0. Okay, then capacitor start discharging in the opposite direction also. Got it? So let Q be the charge on the capacitor at any time instant. let Q be the charge on the capacitor, the instantaneous voltage at that instant, at that time t, across the capacitor will be equal to V equal to Q upon C. So this is the instantaneous voltage. This V is equal to Vm sin omega t. So this instantaneous voltage across the capacitor at any time t when charge on the plates of the capacitor is Q. So it will be V equal to Q by C. C is the capacitance of the capacitor. Mark it as 7.15 equation. Now at any instant you can see the current is flowing in the clockwise direction. Okay, so this plate of the capacitor will be positive and this will be negative. Now we will see, so when a voltage source V equal to Vm sin omega t is applied across it, then charge at some instant on the plates of the capacitor is shown in the figure. Okay, so Q will be equal to CV. So charge on the plates of the capacitor will be equal to Q equal to CV. This Q is a charge on one plate, either positive, either negative, and it is magnitude of charge. We are not considering polarity. We have discussed in the capacitor also. When we describe that charge on the capacitor, what is the charge on the capacitor? It is the magnitude of charge on the one plate of the capacitor. Okay, if we want to find the net charge on the capacitor, so it will be, net charge will be 0 due to positive plate and negative plate, and charge on both plates are equal. Okay, we only calculate this charge on the capacitor means charge on, magnitude of charge on one plate. So Q equal to CV, which is equal to C into what is V? Vm sin omega t. This is the charge on the plates of the capacitor at any instant or any time t. Okay, so derivation of current. So we know that voltage source, it is generating voltage V equal to Vm sin omega t. Now we will find the expression for current flowing through the circuit. So current I is the rate of flow of charges, which is I equal to dq by dt, and Q we have calculated. So put the value of Q, which is C Vm sin omega t, which we have seen in the previous slide. So I equal to D, what is Q? C Vm sin omega t upon dt. This C, capacitance of the capacitor is constant. For a given capacitor, capacitance is constant, and this Vm, peak value of voltage, it is also constant. Okay, so they will come out of the derivative. In the derivative only d sin omega t upon dt. So I equal to CVm d sin omega t upon dt. Okay, so what is the derivation of sin omega t? Cos omega t, and according to chain rule, again omega t will be differentiated and multiplied by the result. So it will be sin omega t multiplied by omega. So it will come out to be omega c Vm cos omega t. This is the expression for I. Now we will solve it further also. Okay, this is the intermediate result for the current. So expression for current for purely capacitive circuit. Now current is in the terms of cos omega t. Voltage is in the term of sin omega t. We have to see the phase difference also. So we have to convert the expression of current in the form of sine function. Okay, so I equal to omega c Vm cos omega t. Okay, so using cos omega t equal to sin omega t plus pi by 2. This is the expression. Okay, so we can also write pi by 2 minus omega t. Okay, we can also write it, but it will not give the expression as we want. Okay, so cos omega t will be equal to omega t plus pi by 2, or we can write pi by 2 plus omega t. Okay, so this is phi, initial phase. So I will be equal to, put cos omega t equal to sin omega t plus phi. So this I equal to omega c Vm sin omega t plus pi by 2. So this pi by 2 is phi, which is initial phase of the current. And if we take phase difference, what is the phase of the voltage? Omega t. What is the phase of current? Omega t plus pi by 2. Okay, so difference of both these phases is pi by 2. So phase difference between current and voltage in the case of capacitive circuit, purely capacitive circuit, is also pi by 2. Now we will see current is lagging behind or leading the voltage. Okay, and this term omega is constant, C is constant, Vm is constant. So it will result in Im. Okay, so where omega c Vm is the amplitude of the current. Amplitude means maximum value, denoted by Im. So Im equal to omega c Vm. So final expression for current will be I equal to Im sin omega t plus pi by 2. This is final expression. Mark it as 7.16 equation. So what was voltage? V equal to Vm sin omega t. What was current? What is current? For purely capacitive circuit, I equal to Im sin omega t plus pi by 2. Okay. Now capacitive reactance Xc. So from the expression of amplitude of current, Im equal to omega CVM. So this can be written as Im equal to, now we have to find the expression for capacitive reactance. In the case of inductive circuit, what was Im? Im was equal to Vm upon omega L. So after comparing it to Im equal to Vm upon R. Okay, so omega L was equivalent to R and having same unit as R. Now we will have to find the capacitive reactance by comparing this expression with the expression for purely resistive circuit. That was Im equal to Vm upon R. So we will, this omega C will go in the denominator of denominator. Means it will, we can represent it as Vm upon 1 by omega C. Okay, this omega C will go up there when we simplify it. Can we write omega C as this? In the denominator 1 by omega C. Okay, so Vim will be equal to Vm upon 1 by omega C. So comparing it with Im equal to Vm upon R. So this 1 by omega C is analogous to this R, as in pure resistive circuit. So term 1 by omega C plays the role of resistance. Term omega L in the inductive circuit played the role of resistance in the purely inductive circuit. Now in the capacitive circuit, term 1 by omega C plays the role of resistance and is called capacitive reactance, denoted by Xc. Okay, so these expressions are somewhat similar. So AC voltage applied to resistor, AC voltage applied to inductor, and AC voltage applied to capacitor. Okay, in the upcoming chapter, in the next chapter, in the next topic, we will discuss the LCR circuit, in which all these three components are used in the circuit in series. Okay, then we will use this formula directly of capacitive circuit, of inductive and resistive circuit. Okay, so that's why we are studying it part by part, component by component. So what is definition of capacitive reactance? So capacitive reactance is the opposition offered by capacitor to the flow of alternating current. Okay, so as resistor is offering the opposition in the case of resistive circuit. Okay, similarly that capacitive reactance, which is equal to 1 by omega C, it is similar to the, it is analogous to the resistance. It is offering the opposition when capacitor is connected. Okay, so that capacitor, that capacitive reactance is the opposition offered by the capacitor to the flow of alternating current, not DC current. In the case of DC current, the result will be different. Okay, so 7.17 equation. So what is the SI unit of Xc? It is playing the role of resistance in the case of capacitive circuit. So SI unit of Xc is also ohm. Okay, so Xc is inversely proportional to frequency, as you can see. Xc is equal to 1 by omega C. So it is inversely proportional to frequency. So omega is 2 pi nu. So 2 pi is constant, so it is inversely proportional to nu. Inversely proportional to frequency, or we can say angular frequency omega. And the capacitance C. Okay, for DC current, now here is the case. For DC current, omega is 0. For DC current, nu is 0. DC current is not varying with respect to time. Also, if it is varying, it is not varying periodically. That's why it has no frequency. Its frequency is 0. It is not repeating its value after a certain interval of time. So it is not periodic function. So it is not, for DC current, omega is equal to, or we can say nu equal to 0. That's why if the term in the denominator is 0, it will become 1 by 0, which is infinite. So Xc is infinite. So a capacitor blocks DC current. So capacitor will block the DC current. Okay, but when we switch on, when we tap the key, current starts from 0 to maximum value. In the case of DC also. Okay, it starts from 0 to a steady value within a very short period of time, in microsecond or milliseconds. Okay, so that micro or millisecond time from 0 to steady current, till that time capacitor start charging. Okay, so before reaching the steady value, the small amount of current, or a current, any amount of arbitrary amount of current according to the time, so current will flow in the circuit. Only when the capacitor is fully charged, then only capacitor will block the DC completely. Otherwise it will not block the DC completely till the capacitor becomes fully charged. Okay, but that time interval is so small, charging of capacitor is so fast, or the approach of current from 0 to the increase of current from 0 to a steady value is so fast, that's why it is not taken into account. So for DC current, omega equal to 0, that means capacitor blocks the DC current completely. Okay, means X is infinite. Now expression for amplitude of the current becomes Im equal to Vm 1 by omega c, and then this 1 by omega c is xc, so we can write Im equal to Vm upon xc. So this is the expression for the maximum current. Mark it as 7.18 equation. So amplitude of current in purely capacitive circuit, Im equal to Vm upon xc. So we can write this expression in the terms of RMS value also. Okay, so from expression of Vm equal to root 2 Vrms and Im equal to root 2 Irms. Okay, so put Vm equal to root 2 Vrms and put Im equal to root 2 Irms. It will become root 2 from both sides will get cancelled out. So it will become Irms equal to Vrms upon Xc. Got it? So phase relationship. So now we will see phase relationship between the current and the voltage. So voltage and current in purely capacitive circuit are respectively, it is given as V equal to Vm sin omega t, which is we have fixed for all type of circuits. Okay, we will take voltage V equal to Vm sin omega t for all type of circuits. We will derive the expression for current according to that. And expression for instantaneous current for capacitor came out to be I equal to Im sin omega t plus pi by 2. Okay, now what is the phase relationship between current and voltage? So phase difference is phase of current minus phase of voltage, means phase of current with respect to phase of voltage. So omega t plus pi by 2, that is the phase of the current, minus omega t. Omega t is the phase of voltage. Okay, so it will come out to be plus pi by 2. In the case of inductive circuit, it came out to be minus pi by 2. This is the phase difference, that is also phase of current with respect to voltage. Okay, so phase of current with respect to voltage came out to be minus pi by 2 in the case of inductive circuit. That means current is lagging behind the voltage. Now it came out to be in the capacitive circuit, it came out to be plus pi by 2. Means current is leading voltage by the phase of pi by 2. It is opposite as in the case of inductor. So what is the conclusion? So taking the difference of phase of current and voltage, current leads the voltage by phase angle of pi by 2, or we can say 1/4 cycle. Okay, you know that 1 cycle is of 2 pi. So pi by 2 is of 1/4 cycle. So current leads the voltage by 1/4 cycle. So phasor and graphical representation of pure capacitive circuit. To draw the phasor diagram of current and voltage, current should be ahead of voltage phasor by pi by 2 at an instant. Okay, so drawing the phasor diagram is easy to show the phase relationship, but for a graph, this graph, it is difficult to understand. That's why phasor are easy to understand. So if you are drawing V equal to Vm omega Vm sin omega t, so at any instant t1, so this voltage phasor is like that, shown by blue arrow. Okay, it is having initial phase, it is having current phase omega t1. Okay, and projection of this voltage phasor is Vm sin omega t1 at an instant t1. Okay, so current is leading. Okay, so if current is lagging, the current vector will be in the downward direction like this. So we'll take minus pi by 2 in the opposite direction, in the clockwise direction. Now it is plus pi by 2, it will be taken as anti-clockwise direction, which is default direction of measurement of angle. We are measuring angle in the anti-clockwise direction. That is taken positive. If we are measuring it in the clockwise direction, it is taken as negative. So current lags behind voltage means minus pi by 2. So it will be measured in the clockwise direction. And in the capacitive circuit, it is plus pi by 2. So it is measured in the anti-clockwise direction. So in the anti-clockwise direction, current leads the voltage by pi by 2 angle. It is shown pi by 2 angle. Okay, so projection of this current will be Im sin omega t1 plus pi by 2. So this is the phasor diagram, phase relationship. Okay, what is graphical representation? Now you can see this is the voltage. Voltage phase of voltage is omega t1. Initial phase of voltage is 0. Initial phase means phi. There is no phi like that in the voltage expression. Okay, so simply sin omega t1. There is no constant term here like this in the current pi by 2. This is the phase, initial phase. There was no initial phase in the voltage. So voltage is starting from 0 as sin omega t graph. So it is starting from 0. Now current is leading the voltage. Means the value of voltage that is reaching at a particular time, current will reach it pi by 2 interval before. Okay, current will reach its maximum value. Voltage is reaching its maximum value at pi by 2 after pi by 2 cycle. And current is reaching its maximum value at 0. So it is reaching its maximum value before voltage by pi by 2 cycle. So it is leading the voltage. Okay, if you want to see the zeros, now voltage is at 0. Okay, minimum value of voltage is equal to 0 at t equal to 0. Okay, or we can say omega t equal to 0. At omega t equal to pi by 2, current is 0. So we cannot say that current value of current is 0 after pi by 2. So current is lagging. No. You can see in this situation, the slope of current is different. It is in the downward direction. And in this condition, slope of the voltage is in the upward direction. So they are not same conditions. So we need same 0. So it is reaching 0 with the negative slope. Current is reaching the 0 value with the negative slope at pi by 2. And the voltage is reaching this pi and having negative slope. The value of voltage is 0 at this pi and having same negative slope as current. So value of this voltage is becoming same as current and under same situations. This is negative slope here. Current graph has negative slope, and voltage graph is having same negative slope after pi by 2 interval, after pi by 2 quarter cycle, or we can say 1 quarter cycle. Okay, so current is leading, or we can say voltage is lagging behind. Same voltage value is coming after pi by 2 cycle or 1 quarter cycle. That means voltage is lagging behind the current. Got it? This graphical representation is difficult to understand, but you have to see the slope or same situation. Okay. So figure 7.8a, a phasor diagram for the current in figure 7.7b, graph of V and I versus omega t. So from figure 7.8a, at some instant t1, phasor I is rotating ahead by angle pi by 2 from phasor V. So both are rotating, but current I, this phasor, is rotating ahead by pi by 2 angle with respect to this voltage phasor. So in figure 7.8b, if we look at time t equal to 0, then current is at peak value. You can see Im, but voltage is 0 at time equal to 0. So current is ahead of voltage. Voltage is reaching its maximum value after pi by 2 interval or cycle. That's why current is leading. Instantaneous power. Now we'll calculate the average power for capacitive circuit also. Okay, so instantaneous power supplied to the capacitor is PC equal to IV. So put the value of I. What was I? I am sine omega t plus pi by 2 in the case of capacitive circuit. So we have written sine omega t plus pi by 2 as cos omega t. It is conversion. So cos omega t can be written as sine omega t plus pi by 2. So we have written sine omega t plus pi by 2 again cos omega t for this expression of instantaneous power. So I equal to V. So I equal to I am sine cos omega t, Vm sine omega t. So it will become I am Vm cos omega t sine omega t. Now we will apply the identity, trigonometric identity. So 2 cos theta, 2 sine theta cos theta equal to sine 2 theta. Okay, so it will become, after multiplying 2 and dividing 2, it will become 2 sine omega t cos omega t upon 2. So in the numerator, it will become sine 2 omega t. Okay, so it will become I am Vm sine 2 omega t upon 2, because sine 2x, or we can say 2 theta equal to 2 sine theta cos theta, or we can write sine 2x equal to 2 sine x cos x. So expression for instantaneous power for pure capacitive circuit is PC equal to I am Vm sine 2 omega t upon 2. Mark it as 7.19 equation. Now PC is equal to I am Vm sine 2 omega t upon 2. So average power. Now we'll take the average. So average of power over a complete cycle will be. So average of this PC will be equal to average of this I am Vm upon 2 sine 2 omega t. So average of this PC will be equal to I am Vm upon 2 sine 2 omega t average. Now average of sine 2 omega t over a complete cycle is 0. Okay, we know that sine 2 omega t, average of this sine 2 omega t will be 0 over a complete cycle. We have calculated it previously also in the inductive circuit also. Okay, so sine 2 omega t is having 0 average. Average of this function is 0. We have calculated in this thing in inductive circuit also or in resistive circuit also. Okay, so PC is equal to, that capital PC is equal to average of this instantaneous PC will be equal to 0 in the case of capacitive circuit also. Okay. So what is the conclusion? Average power supplied to a capacitor over one complete cycle is 0. Okay. In the case of resistive circuit, what was the average power supplied? Im square upon 2 into R. Okay. In the case of inductive circuit, average power supplied to an inductor over a complete cycle was 0 also. Or in the capacitive circuit, it is 0 also. Means power is dissipated only across the resistive component, not across inductive or capacitive component. Okay. So what is the reason for 0 average power for a complete cycle? That capacitor absorbs energy during charging and returns it during discharge. Okay. When current is increasing, capacitor starts charging. When current start decreasing, then current will start discharging. Okay, when current is increasing, capacitor starts charging. When current is decreasing, then capacitor start discharging. Now current will become 0 in the circuit after one positive cycle. Then charging on capacitor will also become 0. Okay, now negative cycle starts. Now current is increasing in the negative direction. in the negative cycle. Now capacitor starts charging in the opposite sense. Now positive plate in the first case, in the positive cycle, will become negative plate, and negative plate will become positive plate. Capacitor start charging in the opposite sense. Okay, now in the maximum current in the negative direction, capacitor is fully charged. Again, when current is decreasing in the negative direction, means it is approaching to zero, then capacitor again start discharging. Okay, so in 1/4 cycle, it will charge and absorbs energy. Now it is fully charged. In the next quarter cycle, it will discharge and it will lose its energy during discharge. So average power supply to capacitor over complete cycle is 0. Now example 7.3. A lamp is connected in series with a capacitor. Predict your observation for DC and AC connections. What happens in each case if the capacitance of the capacitor is reduced? Okay, so DC connection. This is the diagram. So DC source is connected with a capacitor and a bulb. Now what will happen when a DC source is connected? Capacitor starts charging and the current flows for a short time until the charge is complete. Okay, we know that when charging is complete, when capacitor is fully charged, it will block the DC current till it is not charged full. It will not block the current completely. Means it, while it is charging, there will be some amount of current in the circuit and it is decreasing as it is charging and charging. Okay, so it will decrease until it is fully charged. When it is fully charged, it will fully block the DC current. Okay, so glow in the bulb will keep on decreasing, and when the capacitor is fully charged, there is no glow in the bulb. Okay, so bulb will not glow. So when a DC source is connected, capacitor starts charging and the current flows for a very short time. So that short time is for the charging of the capacitor. Okay, until the charging is complete. Once charged, the capacitor has an infinite reactance to DC. As we know, omega is equal to 0 for DC current. Okay, so XC is equal to 1 by omega C will be infinite for DC current. So capacitor has an infinite reactance to DC and circuit will behave like open circuit. So circuit will behave like that it is not a closed circuit, it is open circuit because capacitor will block the current. Okay, so what is the observation? Lamp will not glow when we use DC current or DC source. Okay, so reducing C will not change this observation. So if we will reduce the amount of capacitance also, so it will not change the observation, because whether any value of capacitance is there, it will block the DC source when it is fully charged. Okay, it will block the DC current when it is fully charged. Now when we connect it to AC circuit, AC source, so AC can, in the case of AC connection like this, a capacitor is connected to a AC source. When an AC source is connected, the capacitor offers a finite reactance. It will not offers infinite reactance, because omega C, there will be a finite value of omega. Okay, due to which there will be a finite value of capacitive reactance. It will not be infinite. The current flows continuously and the lamp will glow. So during AC source, during the flow of AC source in the circuit, capacitor will not block completely the AC circuit. It will offers opposition, but it will be finite. That's why lamp will glow. Okay, observation, lamp will glow. Now, in the second part of the question, that what happens in each case if capacitance of the capacitor is reduced. So if capacitance is reduced, the capacitive reactance, now capacitive reactance is inversely proportional to frequency as well as capacitance. If capacitance is decreased, since it is inversely proportional to capacitance, if capacitance is decreased, this capacitive reactance will increase. So if C is reduced, capacitive reactance will increase because Xc is equal to 1 by omega c. So it is inversely proportional to capacitance. So this will decrease the current. If capacitive reactance is increasing in the circuit, that means opposition is increasing in the circuit. Capacitor is offering more opposition, due to which current will be decreased. If amount of opposition to the current is increasing in the circuit, that is Xc is increasing, due to which current will decrease in the circuit. Okay, so what is the observation? The lamp will glow less brightly. Current is reduced, due to which lamp will glow less brightly. Okay, so what is the intensity of lamp glow? It will be entirely based on current flowing through the circuit. Okay, so example 7.4, a 15 microfarad capacitor is connected to a 220 volt 50 hertz source. That 50 hertz is new frequency. 220 volt is which value? RMS or peak or instantaneous? So if it is not mentioned any value, this 220 volt is taken as RMS value. Okay, so now find the capacitive reactance and the current RMS and peak in the circuit if the frequency is doubled. Now second part, if the frequency is doubled, what happens to the capacitive reactance and the current? So let's see the solution. So what is given? C equal to 15 microfarad, which is equal to 15 to 10 to the power minus 6 farad. VRMS is equal to 220 volt. So nu is also given 50 hertz. To calculate capacitive reactance Xc, we need angular frequency omega. Okay, Xc is equal to 1 by omega c. So we need omega for calculating Xc. C is here. Nu is given, so omega is equal to 2 pi nu. So firstly we will find the omega. So omega is equal to 2 pi nu, which is equal to 2 pi into 50, which is equal to 100 pi hertz. So Xc will be equal to 1 by omega c. So Xc will be equal to 1 by, what is omega? 100 pi hertz. So 100 pi into c. What is c? 15 into 10 to the power minus 6 farad. So Xc will be equal to 212 ohm. Okay. Now to calculate the RMS and peak value, so for expression of RMS current, which is equal to IRMS equal to VRMS upon XC from NCERT equation 7.18. So VRMS is given 220 volt. So IRMS will be equal to 220 upon what we have calculated for XC. It is 212 ohm. So 220 upon 212. So IRMS will be equal to 1.04 ampere. Okay. And for expression of peak current, it will be IM equal to root 2 into IRMS. It is the relation between peak value and IRMS value. So IM will be equal to root 2 IRMS, which is equal to root 2 into 1.04. So IM will be equal to 1.47 ampere. This is the peak value of current. Now to analyze the effect of doubling the frequency. If we are doubling the frequency, what happens to the capacitive reactance and the current? So capacitive reactance is inversely proportional to frequency. If we are doubling the frequency, capacitive reactance will become half of its initial value. So new frequency nu dash is equal to 2 nu, which is equal to 100 hertz. New angular frequency will also double because omega is equal to 2 pi nu. If nu is doubling, that means angular frequency will also double. New capacitive reactance Xc dash will be equal to 1 by omega dash c. So omega is doubling, it will become 1 by 2 omega c. So 1 by omega c is Xc. So it will become Xc upon 2. It will become half of its initial value. So Xc dash will be equal to 212 ohm upon 2. And it is equal to 106 ohm. Okay, so it will become half because frequency is doubling. Effect of doubling the frequency on capacitive on the current. So capacitive reactance become half. So current is equal to IRMS is equal to VRMS upon Xc dash. So Xc is becoming half and IRMS is inversely proportional to Xc. So if Xc is becoming half, IRMS will double. because it is inversely proportional to it. So IRMS will be equal to 220 upon 106, which is equal to 2.08 ampere. In the initial case, IRMS was 1.04 ampere. Now it become double because XC become half. Okay, so IRMS initial was 1.04 ampere and XC initial was 212 ohm. That means, so when frequency is double, capacitive reactance is halved and current is doubled. Got it? Now, next example 7.5. A light bulb and an open coil inductor are connected to an AC source through a key shown in the figure. Okay. The switch is closed and after some time, an iron rod is inserted in the interior of the inductor. So now here concept of magnetism and matter chapter will be used here. Okay. So a iron rod is a ferromagnetic substance. It is inserted into the interior of the inductor. Like we insert some material core in the interior of the solenoid. So what it will increase? It will increase the magnetic flux through the coil. Okay. So switch in closed and after some time an iron rod is inserted in the interior of the inductor. The glow of the bulb increases, decreases, is unchanged as the iron rod is inserted. So which option is correct about among these three options? So the glow of the bulb will increase or decrease or remains unchanged as the iron rod is inserted. Give your answer with reasons. So let's see. So inductance of an inductor is given by L equal to mu naught N square AL. So this is the inductance of the inductor. Okay, self-inductance more precisely. Okay, so L equal to mu naught N square AL. NCERT equation 6.15, where mu naught is the permeability of vacuum or free space, L is the length of the inductor, A is the area of cross section or cross sectional area, and equal to number of turns per unit length of the inductor. Okay, now when we insert the iron core inside the interior, so if we fill the inside of the inductor with an iron rod of relative permeability mu r, then inductance is given by, so inductance is mu naught mu r N square AL. So it is when there is no material core inside the inductor, then L will be equal to mu naught N square AL. When there is a material core inside the inductor, then L will be equal to mu r mu naught N square AL. Okay, NCERT equation 6.16. Now, iron rod will be having relative permeability mu r, which is greater than 1, much greater than 1. Since iron rod has relative permeability, the inductance L of the coil increases. So iron rod is having high relative permeability. So inductance L of the coil will increase when we insert the rod inside the inductor. Okay, so XL is equal to omega L. So if L is increasing, inductance of the coil is increasing by inserting iron rod in the core of the inductor, then XL is equal to omega L. So inductive reactance will also increase because it is directly proportional to L. Okay, so consequently the inductive reactance of the coil also increases. As a result, current in the circuit decreases. If what is inductive reactance? It is opposition offered by the inductor to the flow of current. If it is increasing in the circuit, then current in the circuit will decrease. So if current is decreasing, that means the glow of bulb will decrease. So B option is correct option. Okay, so this is all about. Now we will see the summary. For capacitive circuit, IRMS and VRMS are related as IRMS equal to VRMS upon XC, or we can say IM equal to VM upon XC in the terms of peak value, where XC is capacitive reactance. So capacitive reactance is the opposition offered by the capacitor to the flow of alternating current and given by X equal to 1 by omega C. A capacitor completely blocks DC current, that is opposition offered to DC current is infinite as omega equal to 0. So Xc is equal to 1 by omega C and equal to 1 by 0, which is infinite. Average power dissipated in one cycle in pure capacitive circuit is 0. This means capacitor store and return energy but don't dissipated. Okay, this is the phasor diagram for phase relationship between the voltage phasor and current phasor. Okay, figure 7.8. So current is leading voltage by pi by 2 phase. When AC voltage V equal to Vm sin omega t is applied to a capacitor, then current leads the voltage by phase angle of pi by 2. So there are some practice question you have to do yourself. In a purely capacitive AC circuit, what is the phase difference between current and voltage? The average power consumed by an ideal capacitor in an AC circuit over one complete cycle is, options are maximum, B minimum, C 0 or D infinite. Third question, what is the opposition offered by a pure capacitive circuit to DC current? And last question, capacitive reactance is directly proportional to the frequency of the current. Is it true? So thank you. This is all about today's lecture, but don't go anywhere. We have to do the DPP. Okay. So in a purely capacitive AC circuit, the current lags the voltage by pi by 2, lags the voltage by pi by 2, is in phase with the voltage, or lags the voltage by pi. So write your answer in the comment section. So it will lead or lag. Next question, the capacitive reactance Xc is inversely proportional to. So X is equal to 1 by omega C. So it is inversely proportional to frequency and capacitance, frequency only, capacitance only, or voltage and amplitude. Yes, A. In a purely capacitive AC circuit, the average power consumed over a full cycle is Im Vm upon 2, Im Vm 0, or Im Vm upon root 2. So what is the average power consumed over a complete cycle in the capacitive circuit? Which option is correct? No. Purely capacitive circuit is, in purely capacitive circuit and inductive, in both, average power consumed over a complete cycle is 0 in both. In a DC circuit with the capacitor, after charging is complete, when we use DC source, after charging is complete, the current is, yes, P, becomes 0. A capacitor of 15 microfarad is connected to 220 volt 50 hertz source. If the frequency is doubled, the capacitive reactance becomes. So this is conceptual, you don't have to solve. So if frequency is doubled, capacitive reactance X is equal to 1 by omega C, that is 1 by 2 pi nu C. If nu is doubled, what is the effect on Xc? X is inversely proportional to frequency. If frequency is doubled, capacitive reactance will become halved, doubled, quadrupled, or unchanged. So if you have attended the lecture, then don't hesitate to write your answers in comment section. Okay, even if it will be wrong. So thank you.